We will study another very interesting constraint in constraint programming. It's called the element constraints. It's a family of constraints that is used to index an array with variables. But first, let's motivate the usage for that constraint with the very interesting problem, the quadratic assignment problem. The quadratic assignment problem is a problem where you have some warehouses or facilities and you need to place each of them on a specific location. Okay? So for instance, this one will be placed on that one will be placed on that one, this one on this one. Okay, so each of the locations should receive one of the warehouses. But of course, as you can see here on the picture, the locations are separated by some distances. And between each pair of facility, you have an amount of traffic between the facilities. And the goal, of course, is to place two facilities quite close to each other if they exchange a lot. If there is a lot of traffic between the two, then you should place them not too far away in terms of distance for the location that you would choose for them. So how do we model that problem? So the goal is to decide for each facility a location, okay? And the objective function that you will have is what you would like to optimize is for every pair ij of location, you will multiply its amount of traffic between the facility I and j. You will multiply the amount of traffic by the distance between the two locations that you have chosen for these two facilities, I and j. So what this is a two-dimensional integer array. And this D, the matrix D, is also a two-dimensional integer array. But as you can see in this model, xi and xj are the two decision variables. So I need to decide one decision variable for each facility, okay? And for instance, for that one, I will have that x1 is equal to 2, which corresponds to placing this one on the location number 2. And here you have x3 equal to 5 to tell that you have placed this one on the location number 5. Okay? In a model, when you index an array of integer with indices that are variables, that are your decision variables like this one, we call that element constraint. Okay? So this is called two-dimensional element constraints. So let's study the source code of that problem in MiniCP. So first, as you know, you declare the solver. Then you create the array of decision variables. So we create an array of n decision variables. And the domain of each is from 0 to n-1. Then, of course, you pass an all different constraint to say that the location that we choose for each of the facility should be different. And then you will here in this loop, we will build the objective function. So first we create the weighted distance for each of the pairs of facilities, and therefore I create a one-dimensional array of n by n to represent it for every pair of facilities. Okay, so here I have my internal loop, okay, so that I consider every pair k, every pair ij, okay, for every pair ij. So that should be for every pair ij. So what I will do there is that I will multiply the weight between I and j by the distance that separates the two facilities I and j, depending of course of where I have placed these two ones. And what you can see there is that I'm using the element constraint. So this component there is really the modeling of D indexed by xi, xj. Okay, so and the mul is for the multiplication that you have between the two. Then we will, of course, sum all these components. So that sum is the same as doing this. Okay, so we do the sum of each of them. And then what we would like to optimize is, of course, we would like to minimize the total cost, minimize this total weighted sum. That's for the model of the quadratic assignment problem. In the next video, what we will explain is how to implement this very important constraint, the element constraint. In the next few videos, we'll explain that, and we will see a very interesting algorithm for pruning efficiently this constraint, achieving a kind of hybrid consistency. It's not really domain consistency, and it's not really bond consistency. It's a little bit in between.